Good afternoon, and welcome to another exciting episode of The Worst Class Ever, starring Professor Nesgoda. And this week we rejoin after the professor's disastrous attempt at humor with the humorothery rules last week. And this week we'll get some equally cringy moments while he makes a crude and crass joke about the Gibbs phase rule and tries in vain to make the Gibbs-Thompson law comprehensible to anyone except himself. So sit back and relax and enjoy an hour or so of incoherent ramblings from the good professor. Hey everybody, welcome to another week in paradise, otherwise known as quarantine. So on Friday we went through some really important stuff with heterogeneous equilibrium. We hit the common tangent construction, right? And I really tried to stress how important this concept is and how useful of a concept it is. And we will continue to see this over and over and over again throughout this semester. We talked about the construction of phase diagrams, and we left off just before we started with the Gibbs phase rule. So what's the deal with the Gibbs phase rule? Today will be like an all Gibbs lecture because we'll talk about the Gibbs phase rule. Of course, we've been hitting Gibbs free energy pretty hard, but then later on today, we're going to talk about the Gibbs-Thompson rule, or the rule of capillary action, which is really important for when it comes to understanding solid state phase transformations. But let's start out with what is the genius of Gibbs, right? So in the 1870s, Gibbs did something pretty remarkable. He took something that is kind of painfully obvious to us now, but was completely sort of opaque to people before he put such a simple little rule together. And that is, if the question is, if I have two components, how many phases, distinct phases, can I have that are in equilibrium? Is it possible for me to have 4 phases? Right? We know if I have water, just plain water, I know that I can find a combination of temperature and pressure where I have both ice, liquid, water, and water vapor all in equilibrium, right? That's at the triple point of the system, right? And I can do that, I can get there by varying a few degrees of freedom, right? My degrees of freedom in that case happens to be temperature and pressure. Is it possible to have 4 phases in equilibrium in a different substance? What about if I have water and salt together? Can I have 4 phases in equilibrium? I don't know. But Gibbs figured out how to tell us. So we start from this fundamental general conception of equilibrium, right? And this is, again, possible. This definition of equilibrium is possible because Gibbs defined the chemical potential, right? But the chemical potential, the condition, I'm getting all tongue-tied. The condition that we're looking for that defines equilibrium is when the chemical potential of each species is equal in all the phases present, meaning that the Gibbs free energy of species A is the same in phases alpha, beta, gamma, ... on forever, right? The same thing holds for species B. The same thing holds for species C. Be careful. We do not want to say that the chemical potential of A in alpha is equal to B in alpha, right? That is not necessarily true. But from this definition of equilibrium, we can get to the Gibbs phase rule, okay? And it's not that hard to do, but Gibbs doing it was a little bit of a stroke of genius the first time. But Gibbs showed, and then you will do this in the homework coming up, that if a system contains C components and P phases, that is an equilibrium, right? We have the number of thermodynamic degrees of freedom is given by this really simple equation. P plus F equals C plus 2. And hold on for a moment. I'm getting lots of notifications and things. So I'm going to close. Sorry about that. I'll edit it out in post. But anyway, so Gibbs showed that a system, if I have C components and P phases, then my F here, these are my degrees of freedom, are all related by this really simple equation. P plus F equals C plus 2, right? And what do I mean by a degree of freedom? A degree of freedom is an independent variable that we can adjust, right? So for thermodynamics, we're talking about temperature, pressure, the composition of individual components. Now, of course, if we have a binary system where we only have A and B, we can't adjust the composition of A and B independently, right? Because these are mole fractions. They have to add up to 1, right? So if we adjust A, we automatically know what B is, right? However, if we have a ternary or quaternary system, we can adjust more than 1. In general, the number of degrees of freedom related to the composition is going to be the number of species you have minus 1. So in a binary system, we can adjust 1 component independently. In a ternary, we can adjust 2. Okay? So what does this mean? Right? Why is this such a stroke of genius? Well, it tells us sort of something really useful, right? So if we go back to our water example, right? And we have 1 component, right? So if we have the right-hand side then equals 3, and we say I have 3 phases, ice, water, and water vapor, that tells me that I have 0 degrees of freedom. I can't adjust anything about my system. So there is 1 set of variables, 1 temperature, 1 pressure, that allows me to have a triple point. However, if I say I have 2 phases present, say ice and water, that means I now have 2 degrees of freedom. So that means I can adjust both the temperature and the pressure and still maintain equilibrium. I can, for whatever temperature I pick, I can find a pressure that will allow me to have an equilibrium between ice and water. If we are in the world that we live in as material science and generally at constant pressure, we lose 1 degree of freedom. So the constant pressure Gibbs phase rule is P plus F equals C plus 1. Right? But the general phase rule is P plus F equals C plus 2. Now, this is something that people get wrong all the time, right? It's easy to switch up the order. So I'm going to tell you a little mnemonic, a little memory aid, right? And of course, being a good memory aid, this is crass and sophomoric and highly inappropriate, but I guarantee you that once you hear it, you will never, ever, ever forget Gibbs phase rule. And I can guarantee it because when I had someone tell it to me, when I was a first-year graduate student and taking the solid-state materials thermodynamics. It became indelibly etched into my mind. Right? So are you ready for it? Again, crass, sophomoric, highly inappropriate. Paul F's Carla twice. Right? You'll never forget it now. Now, the beauty of it, now here's the real beauty of this, right? You can substitute any two names you want, as long as the P and the C are there, right? It could be Paul and Christopher, Petra and Charles. So whatever suits your fancy in power dynamic. But the thing I really like about it is you can change out the verb, right? It can be any F verb that makes you happy, right? So right now, given the state of the world, right, I prefer either feeds is a good one, right? Paul feeds Carla twice, right? Nice, loving, caring partner, right? Or because we could all use a little bit of, what's the word I'm looking for? Recovery, rehabilitation, no. Reconciliation, that's the R word I was looking for. Paul forgives Carla twice, right? So anyway, a stupid, silly little thing, but you'll never forget the Gibbs phase. So if we consider a binary mixture of two substances, and if we have atmospheric pressure, right, that means we only have, if one phase is present, we have 2 degrees of freedom, right? So if we're in a single phase region on our phase diagram, I can alter the temperature or the composition, right? And stay within that region, right? And I don't mean, when I say vary T, I mean differential, right? T plus or minus dt, right? Or composition, mole fraction plus or minus d mole fraction, right? So we can vary these 2 degrees of freedom and still stay in our same phase region. If I have 2 phases are present, then we only have 1 degree of freedom, right? If we pick the temperature, the composition of both phases is fixed, right? The common tangent construction, right? If I'm at a constant temperature, my Gibbs free energy curves are the same. The composition is completely dictated by the tangent between the 2 Gibbs free energy curves, right? So if we pick the temperature, the composition is fixed. If we say, I want this to be my composition, then the temperature can't be chosen arbitrarily, right? We have to find the temperature that gives us those, the tangent, okay? If we have 3 phases in equilibrium in a binary, then there are no degrees of freedom, right? This is the eutectic point, right? If I want 2 solid phases and a liquid all to be in equilibrium in a binary mixture, I have the eutectic temperature, and that composition is completely fixed by the common tangent to all 3 of the phase curves, right? So really simple, really useful, and that's the genius of Gibbs, right? Now, the amazing thing is in his lifetime, Gibbs was not at all appreciated in the United States. His work was translated into German and French, and he was much more well-known in Europe than he was in the US, because he published in sort of very obscure journals, and the US was dealing with a bunch of other stuff, right? We had the immediate post-World War and the westward expansion, And Gibbs didn't publish in any of the big mainstream science journals at the time. Gibbs published in places like the Journal of the University of Connecticut that no one saw. So while his work was well known and well appreciated in Europe, it was not at all appreciated in the United States. Okay, so coming up, I want to take a little break and look at some illustrative examples on the aluminum carbon phase diagram. And then today we're going to talk about the Gibbs-Thompson rule and equilibrium at surfaces. Okay, so these are some notes that I'm extracting from a previous version of the Advanced Physical Metallurgy class, MSE 5441, that I taught previously. I'm a little big here. Okay. So aluminum is an interesting metal simply because there's not a lot of stuff that's soluble, that has any real appreciable solubility in it, right? So we can see just from looking at these, we know that we can see what the primary alloying elements are going to be. Copper, magnesium, manganese, right? Anything else is going to tend to form intermetallics or have very limited solubility, right? So aluminum iron forms, has a strong ionic type attraction, and we get intermetallics that form, right? But ones with these moderate solubilities, copper, magnesium, lithium, right? These are elements that we end up putting in because they form precipitates that are very useful for strengthening, right? They don't have too much of an ionic character, but they're very hard to cut, and they form secondary phases. So that's the strategy for developing aluminum alloys for the most part, is trying to find things that will give us really a nice fine dispersion of secondary phase particles so that we get a lot of strength, but that we don't end up being too brittle. So one of the most common is copper. So here we see the aluminum copper phase diagram. And so as we see, as we increase the weight percent copper, we go from a single phase region at high temperatures down to this two-phase region where the equilibrium phase is this theta phase. But then we have all these dashed lines on here. So what are these? So these are metastable phases, right? So these metastable phases are actually what we want from an engineering point of view, right? We don't want the thermodynamically stable phase, and we'll talk about why we don't want it in a little bit. But what we're trying to do is this is a TEM micrograph, is get microstructures that look like this. What we want is a very fine dispersion of strengthening precipitates, right? In this case, these are the theta double prime. This length scale here is 250 nanometers, right? So these dark regions are not actually the precipitates themselves. What we're seeing here is the elastic strain associated with having one of these precipitates here. Because these precipitates, these theta double prime, have a lattice mismatch, but it's not so much that we get a completely incoherent interface. What we do is we get a lot of elastic strain around these. And so that's where this contrast is actually coming from in this image. So the actual precipitates are, you know, tens of nanometers in size, right? Okay, so why am I showing you all this? Well, we're going to talk about this system a couple more times. First off, when it comes to a diffusional phase transformation, this is a nice archetypical system because this theta phase, the thermodynamic phase, which is Al2 aluminum 2 copper, is very difficult to nucleate, right? It's an intermetallic compound that doesn't fit well with the aluminum alpha matrix, right? And so it's difficult to start this phase, and we'll talk about why that is in later classes. But what we can see is if we go to lower temperatures, we can form these metastable phases called GP zones that may form. So what are these GP zones? Well, GP zones are just clusters of copper atoms that come together, right? And so they are coherent with the matrix because copper and aluminum both have FCC, right? So this nucleation is pretty easy. They can be dispersed at a very fine scale, right? So what's interesting is if we look at our free energy diagram, right? And this is the real reason why I wanted to show you this now. So here's the free energy for GP zones. Here's the free energy for theta, right? We can see that if we're at composition G0, we can really lower the free energy of our overall system if we can nucleate the equilibrium phase. There's no doubt why this is the equilibrium phase over the GP zones, right? But what's important to note is that even though the free energy of the GP zones themselves is higher, right, we can lower the free energy of the alpha phase quite significantly if we can eliminate the copper. So locally within the GP zones, we're raising our free energy, but we're lowering our global free energy from this G0 to G1. And we're lowering the local free energy in our alpha from A0 to A1. Right? So even though this is a metastable phase that locally is high energy, we can still nucleate it because we reduce our global free energy. Right? The reasons why we don't go right to theta, we'll talk about in later classes. Right? But this is the key example reason I wanted to sort of show you this to show this to you is that it's not always about making things energetically favorably locally, right? It's all about the overall system. All right. So GP zones are metastable over a fairly limited temperature range, right? Because the enthalpy here is high, right? The Gibbs free energy here is fairly high. It doesn't take long before the entropy term takes over. And so at fairly moderate temperatures, these GP zones will dissolve back out. Right? This curve will move high enough up that we're better off just staying in completely in alpha. Okay? But it turns out the GP zones aren't the only metastable phase. We have these other phases, theta double prime, theta prime. Right? What are these other immediate phases? Look like they're larger than the GP zones, right? The theta double prime phase, this is typically what we want when we're trying to develop solid solution strengthening, right? It's a complex, ordered structure here, right? These nucleate at the GP zones heterogeneously, and we'll talk about what that means, of course, later. The the theta double prime, again, this is another ordered compound, and the theta prime is a very large tetragonal unit cell. Again, these are ordered intermetallic compounds, right? But what I want to point out is essentially what we can do is if we start from GP zones, we can progress through a series of these intermediate phases, right? And each time lower the Gibbs free energy of our system a little bit, right? Each time we are going to reduce the amount of copper in our alpha phase, right? We're going to become more and more aluminum rich in the matrix. And what's interesting is each of these is progressively lower in copper, right? It's richer in aluminum than the GP zones, right? Remember, the GP zones themselves are just copper clusters of copper atoms, and these are ordered aluminum copper intermetallic phases, right? So what happens is, as we go here, if we do our lever rule, we'll see that the volume fraction of these precipitates is much higher than the volume fraction for the GP zones, right? Because the amount of copper is going to be, the total amount of copper is going to be increased because it has to leave our alpha phase and go into here, right? So as our alpha becomes less and less copper rich, we're going to have a higher and higher volume fraction of precipitates. Right. Okay, so that's the end what I wanted to show with this, right? Really, I wanted to just highlight a lot of really good information that we can get from these common tangent construction from the partial molar Gibbs free energies, right? These are not abstract things. These are really useful tools that as material scientists, we can get a lot of really important critical information and make predictions about what's going to happen with our system, right? Not just a static, what do we have now, right? But we can use these to guide design. So for the remainder of class today, remainder of the lecture today, I've got two quick topics, one on vacancies and one on the Gibbs-Thompson effect. So we'll start out with vacancies. And I just want to remind everybody of defects in metals. We'll talk about defects in ceramics in just a little bit. And then when we talk about polymer solutions, we'll also talk about defects in polymers briefly. But in metals, we have a couple basics, right? We have either vacancies where we're missing an atom on the lattice site, an interstitial where we have an atom where it doesn't belong in between the lattice sites, right? And these are zero-dimensional point defects, right? We then have line defects, right? Meaning dislocations, right? In this case, an edge dislocation with an extra half plane of atoms here, right? And this defect forms now a line that comes into and out of the screen, right? We also have planar defects such as stacking faults, twins, and other interfaces, right? Or we can have volumetric defects, voids and pores, right? So why am I talking about defects? I really want to focus on vacancies right now for this, right? And why vacancies, we'll get to that. Vacancies are actually incredibly important for phase transformations. But the important thing is that the number of vacancies is fairly significant, right? And they also increase monotonically with temperature. So if we just increase the temperature and we get more vacancies, that means that there's a strong thermodynamic driving force for their creation, right? Now, of course, this immediately begs the question, right? If I'm creating new vacancies in my material, right, and vacancies are atoms that should be, are empty lattice sites where there should be an atom, but there isn't. Where do these atoms go, right? And they go to other defects, right? So grain boundaries, dislocations, and surfaces are all sources and sinks of vacancies. It's really easy to accommodate an extra atom at a surface, right? Especially a free external surface or a grain boundary, right? So as the temperatures go up, atoms essentially hop into, say, a grain boundary, leaving behind a vacancy near the grain boundary that can then diffuse through the material, right? And also, if we have a temperature-dependent vacancy concentration, it also means that we have there's a thermodynamic driving force for their creation, right? Well, what is it, right? Well, essentially, the enthalpy of formation is relatively independent of temperature, right? So the total energy associated with the creation of vacancies is going to be the enthalpy of formation of a single vacancy, which is about 0.6 to 1 electron volt per atom for metals, right? Times the fraction that we have, if this is going to be, if we're assuming 1 mole of our metallic alloy, right? So the enthalpy term is just linear and constantly increasing. However, the entropy term is really what's driving this, because there's a lot more configurations the greater the number of vacancies that you get, right? Of course, it begins to saturate out. So what we have here is a monotonically increasing curve plus a monotonically decreasing curve that initially has a greater negative slope than our increasing portion. But then the slope decays, right? The rate of entropy generation decays with additional vacancies. So we go through a minima, right? And where the change in Gibbs free energy here is at a minima, this becomes our equilibrium vacancy concentration. So what happens as we shift temperature? Well, this stays approximately the same, right? And this has a direct negative temperature dependence. So if we increase the temperature, this curve is going to get deeper down, right? So as this slope becomes more and more negative, this minima, the location of this minima is going to shift to the right, right? So as we shift to the right, our equilibrium vacancy concentration gets higher, but this change in the Gibbs free energy curve also gets deeper and deeper. Right? So meaning that not only do we have more vacancies, we also have more of a driving force for their creation. So I don't know about you guys, but I think one of the amazing things about materials to me is how many properties and issues with material are directly related to the entropy. Right? We don't think about this as normal everyday people, right? Entropy is not a huge consideration in our lives. But as material scientists, entropy is just, and the effects of entropy are so fundamentally ingrained in everything that we do, right? Entropy is completely responsible for the stretch of rubber and elastomers and rubber bands, right? There, and you'll learn in your mechanical behavior class, right? They're basically just entropic springs. When you stretch out a rubber band, you're reducing the number of possible configurations that the cross-linked polymer network that is the rubber band can take. So the driving force to reduce it back to its original shape is just the entropy. You're not stretching any bonds appreciably, right? Here, we have a lot of defects that form in our crystal simply because there's a driving force to move to a greater and greater number of configurations, right? Okay, so what about other defects? Do we have an equilibrium concentration number of grain boundaries? If I take a single crystal, right? So a crystal that has no grain boundaries, and I heat it up, does it magically become a polycrystal? Not necessarily, right? Not I would say, unless it's deformed, unless you did something else to it, it's not going to. What about dislocations? Do we have an equilibrium number of dislocations? Right? Well, we can show this by silicon, right? Silicon single crystals, semiconductors, right? There's a very low dislocation density. If I heat up a silicon wafer, I don't increase my dislocation density. So what about vacancies is so special? Why do we have an equilibrium concentration of vacancies but not of other defects, right? And that's simply because the enthalpy of formation for a dislocation or a grain boundary is too high. This slope is too much, is too positive, right? And so the entropy term, the number of configurations that we gain, is not great enough to counterbalance the large energy penalty that we have to pay, right? So this curve, this Gibbs free energy curve, is always positive. It never goes through any negative regime for those defects. Okay, so why on earth are vacancies useful for phase transformations? Why am I going on about this? So let's go back to what we just talked about, our aluminum copper phase diagram. Here's the curve for GP zones. If I start from a low temperature and I hold in my solid solution region, so in this alpha region, right, we have a single phase, aluminum copper, everything's nice, no secondary phases. If I'm near this silicon solvus line and I quench down, I get about 1 million precipitates per centimeter cubed, right? But if I go up a little bit and I go close to the liquidus temperature and I quench down, I now get 10 to the 15th precipitates per centimeter, right? That's 9 orders of magnitude more. It's not a factor of 9, right? It's not even a factor of 1,000, right? It's a factor of 1 billion. You get 1 billion times more precipitates by quenching from a higher temperature than from a lower temperature, both in the same single phase alpha region. Why is that? Vacancies, right? When we quench down, we essentially are stopping the long-range diffusion, right? And so the vacancies don't have a lot of time to annihilate. So it turns out we need a critical supersaturation of vacancies. They're essential for the processing of many metals and actually many other materials as well, right? Well, why? Right? Because diffusion, right? If we think about diffusional phase transformations, which we're going to spend a lot of time later on in the class thinking about, right? The distance that something is going to diffuse is proportional to the square root of the diffusivity times the time. Well, what's the mechanism for bulk diffusion? Vacancy hopping, right? If I think about diffusing in the absence of vacancies, I need to switch two atoms, right? That's a really hard thing to do. But if I have vacancies there, all I need to do is for an atom to hop into the vacancy and leave another hole behind it, another vacancy behind it, right? So if we look at this example, right? If we look up what the diffusivity of copper and aluminum is, we get 2 times 10 to the 18th centimeters squares per second, right? So really, we'll talk about what exactly this means. You'll probably remember a little bit from 2010, but right, this just gives us an indication of how fast the copper is going to move, how easy it is to move the copper through. If, however, we hold this aluminum copper alloy at 900 seconds for 130 C, we end up with GP zones that are 10 nanometers apart. So we can say that means on average the copper had to diffuse 5 nanometers. So if we take 5 nanometers equals the square root dt, we end up with an apparent diffusivity of 3 times 10 to the minus 16th, right? So because we have a much larger vacancy concentration, we have 2 orders of magnitude higher diffusivity. Because our diffusivity is 2 orders of magnitude higher, right? Because the phase transformation kinetics depends exponentially on the diffusivity, we end up with 9 orders of magnitude higher volume fraction of precipitates because we have a large amount of vacancies. Okay? So what about point defects in other materials? Well, in ionic ceramics, we have 2 really common defects called Schottky defects and Frankel defects. Schottky defects are pairs of vacancies, one on the cation site, one on the anion site, right? If these are both single valent ions, right? In this case, we get paired vacancies so that we maintain an overall charge neutrality in our ceramic, right? If we only lost one, then we would have a partial delta charge, right? And then the other is Frankel defects, where the smaller tip ion, typically our cation, is going to leave a vacancy behind and move to an interstitial site, right? And again, this defect maintains charge neutrality in our ionic ceramic, right? Simple vacancies in ceramics don't occur very often because it leads to a charge imbalance. So most of the time, we're going to end up in these 2 cases, right? In ceramics with very small cations, Frankel defects tend to dominate, where the anion and cation are closer in size, we end up with more Schottky defects, right? And so for homework, I ask you to calculate the equilibrium concentration for Schottky defects, knowing that the enthalpy to form these is roughly about 2 times the enthalpy of formation for a vacancy of metals. So that means generally we're going to have a smaller population of point defects in ceramics than we do in metals, right? Dislocations in ceramics are really interesting because locally that means if I have an extra half plane of atoms in here, which half plane, where do I put it? Which it becomes really confusing, right? Which means if I have an extra half plane, I'm missing this here. So now I've got charge imbalance and like anion and cation repulsions. So dislocations in ceramics are strange beasts that carry charges with them, right? And interfaces in ceramics are very complicated, all because we need to maintain these charge imbalances in ionic ceramics. In covalent ceramics, it's even worse because now I've got to wonder about what do I do with all these missing covalent bonds. Okay, so I know I'm running a little long, but because I don't have an audience, I'm a bit more long-winded than usual. I'm sorry. So anyway, the last thing I wanted to talk about today was the Gibbs-Thomson effect. And so imagine here for a minute, instead of thinking about solid phases, let's think about two gases. We've got a soap bubble of gas beta surrounded by an atmosphere of gas alpha, right? Well, what's the pressure inside this bubble relative to the atmospheric pressure of alpha, right? Well, of course, we have a surface tension here, right? So this surface tension is pulling, right, and compressing beta. So that means the pressure of beta is going to be higher than the pressure of alpha. Why is this important? Well, let's think about activities, right? When we talked about activity before, actually, I pulled that part of the lecture out because it was a little bit too much of a divergence. Well, anyway, remember that the activity of a gas from thermodynamics is directly related to its partial pressure. So if we increase the pressure of beta, we're increasing the activity of beta. If the activity of beta increases, that means the chemical potential of beta is also increasing. So if we generalize this to a solid precipitate, now if beta is a solid and alpha is a solid, what does this imply? We still have a surface tension of this interface. We still have an interfacial energy. So that means the chemical potential inside this small region of beta is elevated. The Gibbs free energy of our phase is going to depend on the nature of the interface between alpha and beta and the size or the volume of this little spherical region. That's pretty far out, I think, right? Because before we only talked about the chemical potential depending on the composition, not about the shape of the phase, right? So the Gibbs free energy or thermodynamic variables are not necessarily intrinsic properties. They depend on the configuration of our microstructure. Let that sink in for a little bit. Our thermodynamic properties of our material are not necessarily intrinsic properties, but they depend on the arrangement in the microstructure. Right? Now you're thinking like real material scientists, not solid state chemists or physicists. Okay, so let's go through a little bit of analysis here. If we go back to the work of expanding a bubble, right? The work done, our pressure volume work, PDV work, has to be balanced by the increase in surface energy, right? If we increase the pressure, we're going to push against the surface. We're going to create a tiny little bit more surface. So that has to be balanced by the surface energy, the interfacial energy, times the new area that we create. So if we have a sphere of radius r, we plug that in, we see that our change in pressure has to be equal to 2 times our surface energy divided by our radius, right? In the Gibbs free energy change of this, because we're changing pressure, we don't have this constant pressure term, so we need our VdP minus SdT. And if we assume that we do this isothermally, our change in Gibbs free energy is equal to, big typo here. The change in Gibbs free energy should be equal to V dP, or delta P. So if we assume 1 mole, right, remember our partial molar Gibbs free energy is the same as our chemical potential. So we can say that the chemical change in the chemical potential of our beta phase is equal to 2 times the interfacial energy times the molar volume of beta, all divided by the radius of our particle. So that means what happens? As we make our particle smaller and smaller, we increase the chemical potential of the beta phase. What on earth does that imply? Well, the chemical potential is a measure of the stability of our system. How happy our different elements are, right? If we raise our chemical potential, we want to have, right? That because an increase in chemical potential gives us a driving force for mass diffusion, right? That was the whole point of all this discussion that we had on chemical potential. So this is really can be really quite significant, right? As R gets smaller, our change in chemical potential for a very, very small particle can be huge. What's that going to do to our microstructure? Well, so here's the Gibbs free energy for beta phase in the bulk, right? Meaning a really, really large particle, right? Of infinite size, right? So we do our common tangent construction, and we see this is the composition of alpha, this is the composition of beta, right? As we make the particle smaller, our composition is going to change. Our beta phase is going to get richer in B. And our matrix phase alpha is going to get poorer in B, right? So we also see that this system can reduce the free energy by taking these small particles and somehow converting them to larger precipitates. So given time, we can reduce our overall energy. And this is called coarsening or Oswald ripening, and it's the last little bit I'm going to mention today, right? What does it also say about the stability of B with increasing temperature, right? As we increase the temperature, what happens to these curves? Eventually, this curve here can get shifted high enough up that the small precipitates dissolve, right? So small precipitates have a lower solvus temperature than big precipitates. So, or equivalently, very, very fine shavings, very, very fine solid will melt before a big chunk at a lower temperature before a big chunk, right? So this change in chemical potential with the curvature also implies that the partial pressure of a material above a convex surface is greater than over a flat surface or a concave surface, right? And so you can sort of see that here why, right? It's a lot easier for an atom to jump off into space, right? To go from solid to vapor or solid to liquid phase if it's out here. If we have a convex surface that looks like this rather than a concave surface, right? So this is fundamental for sintering of ceramics and powder metallurgy, right? Which is one of those processing steps that we'll talk about, right? So this really provides the driving force for how we go from a loosely pressed powder compact to a solid ceramic based on heating well below the melting point, okay? Since the chemical potential of an atom under the curved surface is also changed, that means the free energy for vacancy formation also changes, right? Which means if we can go through it, the analysis is not super straightforward, so we're not going to talk about it, but just here's the final result. Dang it, I got to fix this. There's a typo here. It should not be R. This bottom one should be a capital R, the gas constant, and this is the radius up here. So many stupid mistakes. But anyway, the equation basically says that the vacancy concentration under a concave surface is going to be greater under a flat surface, which is greater under a convex surface. So under this convex surface, we have fewer vacancies than under a concave surface like this. So if we're in our solid, what happens if we diffuse material from a big beta precipitate to a small beta precipitate, right? So if we transfer some DN, a little tiny amount of material, this is going to grow, right? And we already said that the Gibbs free energy change is going to be related to the change of the surface area, right? If this is a really, really big precipitate, the change in surface area here is essentially negligible compared to the change in surface energy of our little particle, right? So what we can get is that our change in Gibbs free energy here is going to, first off, the Gibbs free energy for the system is going to increase if we transfer material from a big particle to a smaller particle, right? And it's the amount that it's going to increase is the change in surface area times the surface energy, right? So what this tells us is that the system can actually reduce its overall free energy by doing this change in reverse. If we move material from small particles to big particles, we can reduce the free energy, right? And that biggest change in free energy is going to be where the change in surface area is the greatest, meaning that our surface area to volume, right? So smaller particles have a much higher surface area to volume ratio. And that for a very small particle, taking away a small amount of volume can lead to a really big change in the amount of surface area that it has. So that means the smaller the particle gets, the greater the driving force for it to dissolve and transfer material to the bigger phase. And that's Oswald ripening, right? So the idea is that given sufficient time and temperature for diffusion to occur, a microstructure with fine dispersion of precipitates will coarsen. We'll end up with larger and more spread out precipitates. In 1958, Lifschitz and Schleozov created a mathematical model for this. right? And it basically shows that the rate at which this is going to occur is going to be proportional to the diffusivity, the molar volume, and the time. It's going to be, and as well as the surface energy of the precipitate. And it's going to be inversely proportional to the temperature. Right? So think about why it might be inversely proportional to the temperature. Right? Does having this T on the bottom actually mean that it's going to coarsen slower at lower temperatures? Maybe, maybe not. I mean, faster at slower at higher temperatures, because there's an intrinsic or implicit dependence of this diffusivity on the temperature as well. Right? But think about in the mathematical model why T might appear on the bottom here. And here's just an example of this where it's really important, something that's near and dear to my heart, ice cream, right? If you have ice cream in the freezer for a long period of time and it's sort of in that almost but not, right, a hot, slightly higher temperature in your freezer where it's still frozen, but it's not super cold, it gets gritty because the small, fine ice crystals that are a signature of really high quality creamy ice cream grow by Oswald ripening to form larger crystals, which you can feel on your teeth and your tongue. And that's the, you know, like in my mind, the worst possible ice cream experience is gritty ice cream. Right? This is almost as bad as ice cream that's partially melted and refroze, where you get those really big ice crystals. But this happens at a temperature just below the freezing, right, over a period of several weeks. There's a really cool little article here from the American Chemical Society, right, on, so it's not a signed reading, but everyone take a look at this. It's only a couple pages long, and it's a lot of fun to read. Okay, so coming up next lecture on Wednesday, we're going to talk about polymer solutions, and then Friday we start solidification. So that's everything for today. Again, I'm sorry we couldn't do this live in person. I'm sorry that I rambled on longer than I was supposed to, but that's life.